All right. Welcome, everyone. It's almost 11:10. Since we don't have CGD Cafe before the seminar, so we will start a little bit earlier. Today, we have our speaker, Justin Small, who is a project scientist at NCAR. He did his PhD at the National Oceanography Center and then joined NCAR in 2010. And he has already done a lot of research over different places. But today, he's gonna introduce his work on the relationship between SST and precipitation in the extratropical area, which I think should be very interesting to a lot of people here. Without further ado, let's welcome Justin Small. Thank you.
Yeah. Been funded by various agencies, most recently by NOAA and the NOAA CVP program as a current project. And I'm going to talk about SST, surface convergence, and precipitation. And I don't know, I'm going to change the subject. I suffer a lot from drying skin. So I get these put these plasters to help my fingers. And it's not because I've been, hitting people like that. So, and that joke probably didn't do well online. So. Back to the talk. There's been a lot of collaborators there, and I want to acknowledge all of them. Going back to the earliest work, I think in this set was from Frank, Brian, and Bob Thomas. And I also want to acknowledge a string of people on the left-hand side there. Many of them commented on an early version of this talk. And maybe I'll orient you on the precipitation climatology, fairly latest state-of-the-art from the IMERG GPM global precipitation measurement satellite constellation, I think that's the word. So this is the latest recent data. And many of you, in fact, probably all of you, are familiar with most of these features. The warm pool, ITCZ, convergence zones in the southern hemisphere. And then in the northern hemisphere, these precipitation maxima lie over western boundary currents, which are like the Gulf Stream, and the Kuroshio, which is shown here, and the Gulf Stream on this side. And then as you go further east in these basins, you're more in the storm track, which can also be influenced by the boundary currents partly. And then in the southern hemisphere, it's a bit weaker, but you also have a storm track providing precipitation there. So a key thing you probably notice from this, and has driven a lot of climate research and views, is that in the tropics you have a much larger region with the high precipitation from the warm pool and the ITCZ. And if you showed the variability, it's also high there. But I'm going to talk on the extratropics. But I'll introduce with a slide on the tropics, going back quite a while to the well-known paper by Gill, 1980. This is looking at the response of the circulation to heating in the atmosphere. And in this experiment, there's a blob of heating basically in this region. This is a spatial map, and the units in X and Y are of Rossby radii, which is about 10 degrees. And this is meant to be heating just off the equator. And the point from this was that in response to the heating, you had vertical motion and near-surface convergence. And it was a response of the circulation to the heating. And the heating coming from evaporation from warm SST. And then another viewpoint, and it dates back to Lindzen and Negum, 1987, but this is from a paper by Back and Bretherton, 2009, kind of updating it, is that the surface convergence can be driven from the surface from SST gradients and boundary layer gradients. And just to illustrate that, I think if you start in the middle, this is the colors are convergence from era 40, near surface convergence. And then the top panel is basically a boundary layer model forced by observed pressure gradients, and it matches quite well to the full era 40 result. And then the bottom is a boundary layer model, but explicitly related to SST. And it's not quite as good as the full boundary layer model, but you can see it captures some of the features seen in era 40. So it's one of the important processes. And actually, there's been an update to that recently by Margaret Duffy in 2020 paper, looking at climate change. So moving now into the extratropical, again going quite a way back, paper by Hoskins and Caroli, which is well referenced. And this schematic was comparing what's happening in the tropics at the top here in response to heating. You have, again, the vertical motion and ascent. You see from the Gill case, you have a low to the west. But then their argument was that in the mid-latitudes, which are these bottom two panels, you could not have that situation. And you have more like downward motion. And the arguments were based on, I think, a typical stratification for the mid-latitudes or part of the extratropics. And I would say it ignored different types of environments in the extratropics, including the western boundary currents, which are this kind of very warm surface, less stratified, particularly in summer, more like the tropics. And it also did not account for storm tracks. And in subsequent, there's a lot of literature dealing with how storm tracks affected this. So this is more the linear response. Then another well-known paper by Minobe, 2008, was trying to explain convergence and precipitation in the western North Atlantic, essentially connected to the Gulf Stream and Atlantic current. I've forgotten the name now. But the point was you have convergence. The contours are the warm water of the Gulf Stream. So you have convergence of the warm water seen in satellite data and ECMWF analysis. And it related to the Laplacian or curvature of sea level pressure, and also related to the Laplacian of sea surface temperature. And so there was part of this paper was an argument that the Laplacian of sea surface temperature was important in driving this convergence. And it was mainly based on a spatial resemblance between these maps. If you look in detail, they're not exactly the same, but they're kind of comparing this field with these fields here. And there's also a rain rate maximum over the Gulf Stream and the boundary current. But this, and so this process, I forgot to discuss in the previous slide, but this is saying you go from SST gradients to pressure gradients to surface convergence and then to convection. That's the process here. But later papers argued against that, and they found out that if a lot of this surface convergence was due to a few extreme events, basically strong fronts and storms. In the left panel, a paper by Larry O'Neill et al. Found that if you removed just 5%, the strongest 5% storms, you go from convergence to divergence. So you flip the sign of what's happening near the surface. And then on the right, the paper by Reese Parfit and Hyades Sio basically identified that all the near-surface convergence occurred in atmosphere fronts, which is actually shown by these negative values here, which are convergence on frontal days. So this may be regarded as SST gradients affecting synoptic storms, affecting atmospheric fronts which come with the storms. In the front is convection, and associated with that is surface convergence. So this is very indirect from SST. There's a few steps in between. And another framework I'm going to discuss here, and a few people in the room are very familiar with this, and actually Brian Medeiros mentioned this in an exchange talk. Hasselmann, who won a Nobel Prize for this and other work, I think the first person to include stochastic theory in climate models. So this is, under the overall title, there's models of air sea coupling with stochastic variability, either in the atmosphere or ocean. So it starts with the theory from Hasselmann, and then Frankenmuhl and Hasselmann came, I think, a more accessible paper, applied that to look at how the mixed layer temperature and sea surface temperature evolved and responded to stochastic forcing, which induced a low frequency component to the sea surface temperature. Then, following that, Barsugli and Battisti came up with basically a coupled version. The previous two papers were looking at the ocean mixed layer responding and equation for the ocean temperature. Barsugli and Battisti had atmosphere temperature evolution in it as well. It was strongly coupled. And then another paper by Frankenmuhl et al. Used basically the mixed layer model framework to look at feedbacks, air sea feedbacks. And then since then, there's been a whole slew of papers, but I'll probably point out this one by Wu et al., Wu, Kertman, and Peguillon, introduced stochastic ocean noise for the tropics. And you get a different response to just with the atmosphere noise, which I'll show in the next slide. And then after that, Kertman et al., first paper to kind of hint at this might be happening in climate models. And I'll go back to that. Stu Bishop led our paper on the scale dependence of this air-sea interaction. Then we had a paper looking at what drives the air-sea fluxes, which is related to this question. And then most recent papers, I think one by Lucas Lorindo and our group, looking at scales in more detail from very long climate simulations of the air-sea interaction. And then Patrizio and Thompson, again, applying the stochastic model. They've had some kind of curious findings on longer time scales. Things change. I won't have time to talk about that. I'll just illustrate this, an example from the paper by Wu et al. That if you look at correlations between SST and turbulent heat fluxes, you get a very different picture from if you force it with stochastic atmosphere noise, which is on the top, to ocean noise on the bottom. So with the atmosphere noise, you have this negative, follow actually the solid line. You have a negative correlation at zero lag between the SST and the turbulent heat flux. And here, positive values of turbulent heat flux are out to the ocean. But when you include ocean noise, it flips the sign at zero lag, again, this solid line. You get a positive correlation between SST and turbulent heat flux. So in some of the later slides, I'll show this correlation of SST and either latent heat flux or precipitation to compare with this framework. And we've done a lot more than just these point correlations, but that's what I use to illustrate the point. So the overall aim of this talk is to understand the connection between SST and precipitation, as the title says, I particularly want to assess how well it's represented in CSM, especially the parameterized convective precipitation part, which seems to be the part that responds to the SST. I'll add a note here, and it's relevant to some recent discussions around here. This is using an older version of the model, CSM1, and my main reason for this is I'm using high resolution atmosphere and ocean, and that's the last time we had that running. But there are some things we could learn from later versions of the model, even without the highest resolution. And I'll come back to discussion points on that, but please bear that in mind. And in fact, I'm a bit worried that this talk will go on a bit long. I really want to come back to the discussions. I hope somebody will tell me to speed up or finish if it's too long. These are the kind of discussion points I want to come back to. What have we learned about convective parameterizations? Would these results change in later versions of CSM? Do you expect changes in very high resolution models? How good is the IMO data set, this satellite data set, that's actually a merged data set, and other questions. So I'll structure the talk like this. I'll start with SST and surface heat and moisture fluxes, or buoyancy flux. So these are things which are driving precipitation. I'll then talk about explicitly SST and precipitation. Then I'll come back to SST and surface convergence. I won't have time to talk about the remote response. I tell you there's a lot of papers on that, which take too long to go through them, and I prefer to come back to the discussion. And the model data sets that I'm using, CSM1, a high resolution, is 1/4 degree atmosphere, and it's 0.1 degree in the ocean. One thing I'll point out, but both these model experiments were with spectral element dynamical core, for CAM, so that's actually applicable to the current tests. So use CAM5. The deep convection is modified Zhang and McFarlane. To my best of my knowledge, the PBL scheme is from Park et al., a UW scheme. So that's changed quite a bit, the PBL scheme. I'll be using the ERA 5 reanalysis. It's about 0.31 degree native grid, convection from a TICA scheme, and obviously it includes data assimilation. So there's questions I'll come back to is how much of the ERA 5 results are due to data assimilation versus the model background to it. And I'll just say a lot of this presentation used monthly mean data, except where it doesn't. And then I'll be going to satellite engage precip, the IMO product. It's a sophisticated product using data from GPM and other sources. It's output on a 0.1 degree grid at high temporal resolution. I think it's a discussion point on whether it really resolved things down to that scale. We'll come back to that. I also looked at previous data sets, and a kind of history notice. Before we looked at IMERG, it was very hard to see some of the signals I'll show in this talk. So IMERG has kind of transformed this. So that's a note. And one of the kind of obvious things is GPM and IMERG, it extends to higher latitudes. TRIM was limited to about plus or minus 40 degrees. So GPM has extended it. I'm not sure what the limit is, maybe 65 or something. And there's results from literature. And then I'll also talk about surface fluxes, 10-meter wind vectors. OA flux is a well-known optimal interpolation to get fluxes. JF403, it's a high resolution, 1/4 degree, mostly satellite-derived estimates of fluxes. CCMP is a merge of the wind vectors at 10 meters. So I'll start with the surface heat and moisture fluxes, and I'll show latent heat flux. You can convert that to evaporation pretty readily by dividing by the latent heat of vaporization. So you can think it's like evaporation. And so I said I'd be doing these correlations between SST and turbulent heat fluxes or precipitation. So this is it. This is done grid point by grid point. And the top panel is this estimate of the real world. I wonder what the best way to describe it is. It's not an observation, but it's derived from observation, JF403. And what you see, the positive correlations, you noted in the tropics, even though I've removed a lot of the ENSO signal. It still interacts this way in the tropics, even without ENSO. And then you get these signals in the extratropics a lot, for example, in the northern hemisphere around the western boundary currents, southern hemisphere around the ACC. I should have pointed out the current in the southern ocean. And at another point, I'm forgetting now, maybe I'll come back to it. This is the high resolution CSM, and what you see is qualitatively it's very good. Matches very well the J403. It's stronger magnitude of correlation, but it matches well. And this is low resolution, and the way I've done this is look at sensitivity to ocean resolution for this particular plot. The atmosphere resolution is the same between these two panels. And you see the changing ocean resolution is the key thing, that you lose the signal in the extratropics. And the point I just forgot to come back to me is that actually if I showed this plot with ENSO in it, it'll be stronger along the equator as you expect. But interestingly, it doesn't change much the extratropics. And that is not saying ENSO is unimportant for the extratropics. It's just saying for this is zero lag correlations for this particular metric. It's actually dominated by the variability in SST locally, for example, in the western boundary currents. And the signal's so large from that, it probably masks the signal from ENSO. And again, it's zero lag. Some of the ENSO signals be lagged. So that's an aside. Okay, so now I'm going to go from that to precipitation. So we saw those positive correlations in SST and turbulent heat flux. This is from the literature. Again, Wu et al. Mentioned before, this is a correlation between SST and precip from older data set CMAP. And you see that it's dominated in the tropics by these positive correlations, suggesting ocean driving. In higher latitudes, it's negative. And then from Trember-Finchet, this is a motivating paper for some of the work I've been doing. They looked at GPCP and saw a similar kind of thing. So this is actually for boreal winter. And so you have the high positive correlations in the tropics. There's some positive correlations away from the tropics. And I'll point out the color bar is a little bit difficult to read. But there's some greens here which are actually negative here, which may be relating to this kind of thing. And then in CAM3 and CCSM3, the general takeaway point was that the correlations were too high, not just in the atmosphere model. And you can imagine an atmosphere model doesn't have the perfect coupling, but in the coupled model, there's also higher correlations. So, is that a problem with the model? Or is it some of the observations? And has it changed in more recent versions, model versions? I'll go into that. This is now from the high resolution CSM again, so now CSM1. And the top left is correlation between SST and convective precip. I've done this removal of ENSO again, but you still see positive correlations in the tropics. But you see signals in the extratropics, like here, here, and here. And the other thing I want to point out here, I'm looking at convective precip, and there'll be a slide somewhere in this talk which show you don't get this response with the large scale part of the precip. It's the convective. So I'll be focusing on the convective. The previous slide showed total precip. So I'll be showing total precip a bit later just to make it consistent with the previous slide. If you look at just the variability or standard deviation of convective precip from the run, well, it's high where you expect in the tropics, warm pool, ITCZ, etc. It's actually reasonably high in these boundary currents and extratropics. It's about a half. The magnitude of the standard deviation is about 1 up here, and it's 2 in the ITCZ. So why do you get such large variability in the western boundary currents and extratropics here? In particular, if you do a regression of convective precip onto SST, so units are millimeters per day per degree C, there's a big change from the tropics, and this is a nonlinear color bar, so it's about up to 4 in the tropics, and it goes down to about 0.1 or 0.2 in the extratropics and the boundary current. So but actually, when I saw this, I thought, oh, well, this is really a sign of it's not very important in the extratropics. It's such a weak response to the SST. However, the variability of SST is much higher in the extratropics than in the tropics. Here in the model, it's between 2 and 4 degrees standard deviation. I think in the observations, maybe about 2 degrees. And then in the tropics, it's much weaker, 0.25 or less. Again, I've removed ENSO for this. So it's kind of well known. In the tropics, you do get a large precipitation response to small amounts of SST variability. In the extratropics, you get a small response to SST, but you get a large SST variability. So that's kind of my interpretation of this. So this is all from the model. And the next few slides will be comparing with ERA5 and IMERG. Similar high-resolution model. So I'll go through those. And this is starting with convective precipitation and SST, again, like the previous slide. It's a high-resolution CSM at the top, low resolution in the model, ERA5 at the bottom. And you see the same kind of features I showed on the previous slide in the high-res CSM. And the low-res, slightly weaker, but it's actually stronger in both versions of the model in the extratropics than ERA5. And high resolution has the strongest correlation. If I apply a very sophisticated filter to remove tropical influence, which is that, you can focus on the extratropics. That's a joke. And I mean, hopefully you can see from this that the correlations in the CSM in high res and low res stronger than in ERA5, the bottom panel. So that's one result. And we can talk about why later. This is now large-scale precipitation. And this I find harder to interpret. I find in general they're more similar between the model versions and ERA5. You don't see much of this response to SST in highly variable SST regions. And again, if you apply this filter, there's if you look in detail, there are differences, and I can't explain them. But for example, it's kind of very negative in the low-res CSM, whereas in ERA5 and high-res, it's not so negative. But maybe more importantly here, now I'm going to look, this is total precipitation, which is what is shown in the previous literature. High-res at the top, so just point out, you still see in the total precipitation in the high-res model features along the boundary currents in the Southern Ocean. Low-resolution CSM, then ERA5, and then IMERG on the bottom. And there are hints of the extratropical signals in ERA5 and IMERG, but they're much weaker. I'll point out, for example, here in the Southern Ocean, get some positive correlations in ERA5 and IMERG, but it's a bit noisy and much weaker than the model. And a question we can come back to at the end, ERA5 looks quite like satellite observations IMERG. How much of that is by design? You know, what aspects of data assimilation are driving that? Again, you can focus on the extratropics, and you see it's stronger in the model than in ERA5 and IMERG. Then I'm going to shift gears a bit and look at scales of motion. This is using wave number frequency spectra from Lucas Lorindo. And so in these panels on the left side is the frequency. Look over here, the equivalent period in days. And then at the bottom, I've cut off the label here. This is wave number. And you need to look at the wavelength, which is above there. And I'm relating divergence and precipitation. And the divergence is at 10 meters. This is kind of relevant to the next thing. And the left panel is stratiform precipitation, or large scale. And this is era 5, I should point out. Middle panel is with convective precipitation, and the right is the total. And I'm going to look in this kind of area here, because I know from the work I've been doing, this is where the ocean is affecting the atmosphere in the extratropics in wave number frequency space. It's a bit larger than the mesoscale ocean scale. And so you see this kind of localized maximum, and it happens for periods of over 30 days. So it doesn't happen for the short time scales, which are up here. It's happening later on for longer time scales, 30 days or more. And then I'll also point out this band here, this is more the atmosphere dynamics. Here, this is low wave number, not so much affected by the SST. So if you look in this region here, you see a signal in convective precipitation. If you look in the same region of stratiform precipitation, it is not there. The whites mean near zero. So we only see this response of precipitation to near-surface divergence in the convective part. That's in era 5. And then Adam Harrington passed me this plot from his paper on the right. Hopefully you can see I haven't made it too small. But it's looking at the dependence of precipitation rate, which is on the left here, on basically vertical motion at 850. It's scaled, but 850 hectopascal omega is the key thing here. What they found from that paper, and Adam was saying to me, was that it's the stratiform part was responding to the vertical motion, which is related to the convergence. So this might be a bit contrary to this result on the left, where I said it's convective part. And so a couple of reasons I could think of this. One is different data sets. One is on the left is era 5, on the right is CSM2. But I think maybe more likely it's, this is vertical velocity at 850 hectopascal, and this is near surface convergence, and they may not directly relate. In fact, I think I know that. So it depends where you're looking in the column on what is the control on the different types of precipitation. And I'll just quickly say there's kind of an interesting paper by Ben Kirkman et al., where if you have an ensemble of atmosphere states forced by an eddying ocean, and then you take the ensemble mean of the atmospheric states, and then you do the correlation between SST and convective precipitation, you get much higher values than for just an individual ensemble member. So maybe this is obvious, and I think the statement in the paper is that in the interactive ensemble mean, effect of natural variability not related to ocean state has been removed, and the response to the SST is stronger. But what I've found is, and so that's a very interesting result. But the interesting thing to me is that the way the atmosphere is responding to the SST may also involve high frequency variability, which is a part of the natural variability. So there's some interesting questions here about how in this top panel, what exactly is happening. Is it some kind of linear, steady response to warm SST, or is it actually the storms being somehow maybe anchored or fixed to the SST, so that when you take the ensemble mean, you still see the effect of the storms. So that's kind of an interesting question. And I should now speed up. I'll talk about SST and surface convergence, and then we'll go to the discussion. And some results from a recent paper where we looked and we revisited this question of does the near-surface wind convergence of the Gulf Stream, does it relate to these boundary layer pressure gradients or not, or is it fronts in the atmosphere? And this is basically the kind of model that you have from the Lindzen-Negum approach, and then these subsequent papers, and this is actually from Margaret Duffy's paper, that the divergence shown on the left up here is related to the Laplacian of air temperature. And then we did an empirical relationship between Laplacian of air temperature and Laplacian of SST. So this is kind of semi-empirical. And the result you get from this was if you force this model, basically these two equations with kind of appropriate coefficients, which you have to fiddle around with, the contours in this lower left panel are Laplacian of SST, and the colors are the near-surface convergence. And by design, they overlie each other because of this relationship in the top right. And you get these kind of amplitudes. And then you can compare it with what actually ERA 5 is showing. So the top panel now is ERA 5 near-surface convergence. I've filtered it. There's a key step here. This panel is filtered to scales less than 500 kilometers. And then the bottom is the boundary layer model from the previous slide. And the point is they're similar magnitude. They're not exactly the same. There's some phase shifting going on, but it's capturing a lot of the main processes. This is a long-term mean. And again, I've filtered the ERA 5 data. And so what it means is this response to Laplacian ST is affecting small scales. And there's a kind of assumption that the atmosphere fronts and synoptic storms may be affecting slightly larger scales. And you can look at the variability. This is similar to what I showed before, but now between Laplacian of SST and near-surface divergence. I didn't say that this is a coherence diagram for those familiar with spectral methods. Varies between 0 and 1, like in the previous slide. So the stronger coherence is in the same region I highlighted in the other slide, previous slide. And then actually you can then do the next step in the link. So you've gone on the left from Laplacian of SST to divergence. Then you can go from divergence to convective precipitation. This is from the previous slide. And you see it's in the same region that you get maxima. So I think this is kind of strong evidence that you are having a response of convective precip to the Laplacian of SST. It's just one of the processes, but it is and just it's probably the final result I'm going to show. In the long-term mean, the high-resolution CSM captures quite a lot of the convergence at the lowest level they see in ERA 5. So that's what I'm comparing here. And at least some of that is related to the Laplacian of SST shown on the left. And there's a response in precipitation. I'll have a comment on that in a minute. You miss some of it. This is the low-res CSM at the bottom. You miss some of the convergence signal, but not all of it. And I think that's because you have synoptic storms and atmosphere fronts in this low-res CSM, and they're contributing quite a lot of the convergence. And then the ocean fine structure, which is shown by this kind of stuff here, is adding to the fine structure of the convergence. So there's different scales. I just want to make a comment on this. I'd like to make myself, or get someone to help me, a full moisture budget to compare the roles of evaporation or the heat fluxes at the surface and of the surface convergence to precipitation. So I showed, say on the right panel is precipitation, but exactly how much is that coming from the near surface convergence versus how much coming from evaporation, and how do they feedback are things I'm interested in. So I'll summarize that I'm not sure if this is the major result, but I'll put it at the top here. A process related to the Lindzen-Negum gradients of SST affecting surface convergence does operate in the extratropics, but it depends on space and time scales. That's what I showed with the spectra. The large latent heat flux stroke evaporation anomaly seen over warm SST in high resolution CSM and satellite analysis is not seen in low resolution in the extratropics. And then in high resolution CSM and ERA 5, the response to the mostly mesoscale extratropical SST is solely in the convective part. And I think people in the audience probably know why that is. I talked to Rich Neal about it. It's explaining a little bit to me. However, the convective response in CSM is much stronger than in ERA 5 and IMOG, but is qualitatively consistent. And finally, the storm tracks and fronts respond to SST, thus influencing precipitation in winter. I didn't go into that in detail, but the extratropical winter precipitation is almost solely in fronts. That's work done by Reese Parfit and others. But then there's this kind of interesting paper by Ben Kirkman et al. Showing that if you remove a lot of the natural variability, you get a stronger signal. So it's kind of interesting. And I want to leave it with a discussion point. So these were mainly results from CSM1. Things have changed to CSM2 and 3, including the PBL scheme and club being introduced. But I don't think the deep convection has changed much. And one point is the general thing that the convective precip in the model was higher than ERA 5. That was seen at the low resolution of CSM1. So we can look in low resolution CSM2 or 3 development to see these metrics, even though we don't have a high resolution coupled CSM2 or 3. And if anyone has any comments, please go ahead. These are the, in fact, I'll stop talking and thank you. And if you have any comments on the talk or on these discussion points, please let me know. Thank you.
All right, Q&A session. Do anyone have any questions for Justin? Okay, yeah. Do we already turn on the CD mics? Okay, yeah.
I was just wondering, a lot of the comparisons you did between the model and observations were correlation coefficients, in particular where you showed that the correlation was higher in CSM than in ERA 5. I'm just wondering if you've looked at that in terms of regression coefficients and whether the magnitude of the relationship is right and there's just not enough noise unrelated to that, or whether the magnitude of the relationship is wrong.
Yeah, that's a good question, and I need to do that. The results with the regression were actually done very recently from CSM, and I want to add it for ERA 5 and IMOG. Some of those results from ERA 5 and IMOG were from my collaborators, so I have to ask them to do it. But I can answer something. I went back, there's some literature on response to eddies in boundary currents that are in terms of millimeters per day per degree C. And they were consistent with what I was finding. It's about 0.1 to 0.2. So it's not large compared to the tropics. They do have a larger variability. But I would like to make those particular results more robust, I think. Thank you.
Other questions? Others?
You can do Meg's first.
Okay, so this is a question online from Matt. Really interesting talk, Justin. I'm curious about monthly versus daily precipitation data. Do you expect any big changes in the correlation strength with SST if you are using one or the other?
Yeah, I think that's a good question, and some people have looked at daily data. For the extratropics, from the kind of studies we did related to the stochastic model, we know that as you go down to daily timescales, the atmosphere is forcing more, due to the synoptic atmosphere variability, by which I mean the turbulent heat fluxes are more driven by the atmosphere when you go down to daily timescales. So one of the reasons I was using monthly data for a lot of the plots is I knew the ocean was playing a bigger role on monthly timescales. So I think the extratropics might be harder if you go back to daily timescales to keep with this synoptic variability. But there are people that have looked in the tropics at daily data, and Rick Carbone from NCAR was one of them, and then Elizabeth Thompson from NOAA, who is here, and collaborators are looking in the tropics and going back to the high-frequency data, looking for signals.
Alice, go ahead.
I was going to say, one of the questions you brought up near the end was about the impact of evaporation versus convergence and stuff like that. And I guess it made me think about some polar studies where they've used water tracer tags to understand, if you're getting more evaporation locally in the future. And I was wondering if you'd looked at any or considered experiments like that to kind of answer that question.
Yeah, that's a good question. I know some literature that's kind of been tagging parcels in the atmosphere. And my current project with collaborators, Reese Parfit in particular, has been doing that kind of thing. So exactly, tracing where these signals and precipitation maybe come from. Here. I haven't done it, but I think collaborators might be doing that.
Thanks.
Okay, yeah, go ahead.
Thanks, Justin. I'm wondering, if you were to do this with, say, a convective resolving or a convective permitting atmospheric model, do you think those same relationships would hold up? Or do you think that this is sort of maybe some of it's coming from the parameterizations that are built into our convective and our large-scale precipitation schemes?
Yeah, I think that's a big question, and I'm not sure if you know, maybe Yang knows more, things like LES. But what I thought was an encouraging, other people can respond in a minute, what I thought was encouraging when I looked at the ERA 5 and IMOG data was that there was some similarity to the IMOG, mostly satellite or gauge data. It might have some reanalysis of some kind of background, but it's mostly observations. It's qualitatively consistent with the CSM and ERA 5. So that was encouraging that something was happening right in the high-res CSM, but it's no doubt not perfect. I think it's an open question of whether there's errors of the model or the observations.
Okay, yeah, go ahead.
I wanted to ask about the what the issue is for you with the interactive ensemble.
Well, I understand that using ensemble mean remove this natural variability not connected to the SST, so you damp down the influence of the natural variability. The point I was making, and it's not really clearly thought out, but there's arguments that the way that the atmosphere responds to SST in the extratropics is via atmosphere fronts and synoptic storms, which are there's certainly variability. I don't know if you call them, well, they are natural variability, but in turn they're influenced by SST. So when you take the, I think the ensemble mean, you may not be just removing all natural variability or averaging it out. You might actually have some kind of fixed frontal response to SST, might be there in the mean or something, or some fixed response of cyclones to SST, maybe there in the ensemble mean. That might be part of the response of the atmosphere to SST, rather than totally removing or really averaging out the variability. And I think there are some arguments related to that. that there's a residual, some people call it a residual effect of storms when you average out over a place like the Gulf Stream. They don't average out to zero for certain variables.
I think that's what you want. In the interactive ensemble, you're trying to get what is the true coupled
Yeah,
feedbacks,
yeah.
taking out the atmospheric noise. Yeah, we
Yes.
can talk more
Yeah,
about
no,
it, but
may
it seems
not.
to me it's what you want.
Right, yeah.
Okay, we have Jerry first, and then we have.
It's really interesting to talk to us, and I like the way you were looking at these two different observational data sets, the IMERG and the ERA SST data, and I think it's nice they're similar, but I noticed the one big difference in when you had the correlations for the precip was in the Indian Ocean, tropical Indian Ocean.
Yeah.
And I was wondering if anybody else has noticed that, or if you had any thoughts about what's going on there. I mean, there are two different time periods, right? So IMERG is later than the ERA. So maybe there's more, and there's been a big warming trend in the Indian Ocean over that time period, so maybe there's something going on with the trend there that makes them different, or differences in the observations, or?
Well, one point, it's era 5, and I think that's has up to recent, current reanalysis. So they might, I need to check this, but they might be the same time period. I think they were, and maybe labeled, I don't know. Let's see if it's mentioned. It's possible I didn't write it down. I didn't put the time, but they did tell me at some point.
I think it was in the titles.
Yeah,
I think you had it in the titles of the panels.
Yeah.
1990.
Oh, era 5. Let's see if it's in the era 5. Oh yeah, era 5, 90 to 2005, and sorry about this. I'm 2001.
There we go. That's when you really see the big difference in the Indian Ocean.
Right. Yes. And so you're exactly right, Jerry. They are different time periods. And well, I had this naive question. I don't know if the precip from era 5 is meant to look like observations in terms of is there precip, anything related to precip that's assimilated? I think there's humidity. I don't know anything more directly related to precip. So maybe this is an encouraging result for era 5 that apart from the Indian Ocean, it looks similar to IMERG, or maybe this is just obvious, this is what it should be. And I don't know. I could maybe just have to ask someone that knows more about era 5. But yeah.
I think it's interesting that by doing this comparison, this is really good, right? Because this highlights issues with observations for different time periods, and so there are a number of things going on, but I think it's good to have these two observational estimates to really give some context for it.
Yeah, I think if we didn't have IMERG, I'd be questioning era 5. Just naturally, just question things. So yeah, having that data set. And these co-authors, Xiaoqi, Wang, and Ping Chang, they looked at older data sets like GPCP, and they missed some of this extratropical stuff. They got the tropical stuff okay. So yeah, looking at different data sets is very beneficial.
All right, it's already the top of the hour. Let's thank Justin for. So we don't have time now. If you have other questions, just ask Justin in person or email him. Yeah. All right. Thank you so much. We don't have seminar next week because of AGU, but we are.